Hello everyone, welcome to the screencast videos for CHY 103 or General Chemistry. I'm Riyasad and I'm here to help you with the basics of chemistry. Oxidation is the process where an atom or an ion loses its electrons. Reduction, on the other hand, is the process where an atom or an ion gains electrons. Usually when trying to figure out which atom or compound is oxidized or reduced, we need to make sure that we use oxidation numbers. Oxidation numbers and changes to them also help us find out about cathodes and anodes in galvanic or voltaic cells, which is very useful in chemistry. Any element or compound that undergoes reduction is known as the oxidizing agent. Similarly, any element or compound that undergoes oxidation is known as the reducing agent. Students usually have problems with figuring out oxidation numbers. Once that is figured out, every other concept is easy to grasp. In this video, we will have a look at how to figure out the oxidation number of atoms of elements or compounds. We will also look over ways to figure out oxidizing and reducing agents in any balanced reaction. To start off, we need to keep some things in mind. People usually memorize these, but knowing a few is good enough, to be honest. The first one would be that there are two types of oxidation numbers. One is the unit oxidation number, and the other is the total oxidation number. Unit oxidation number is the oxidation number of an individual element in its atomic or ionic form. The other type of oxidation number, or the total oxidation number, is the oxidation number of a compound as a whole, which includes the oxidation number of every single type of atom in that compound added together. Now, the total oxidation number of neutral elements and compounds will always be zero, just like their charge. So if we have sodium chloride, or NaCl, or even oxygen, or O2 in its diatomic state, which is its natural state, the total oxidation number of both of them is going to be zero. Similarly, oxygen is not present in its natural state sometimes. So if we have phosphate, for example, we do not have oxygen in its natural state here. So the oxidation number of oxygen for these cases is going to be -2 at all times. The only exception to this would be when we have peroxide, or H2O2. This is when oxygen will have an oxidation number, a unit oxidation number of -1. When we talk about oxidation numbers, we are generally talking about unit oxidation numbers. We only use total oxidation numbers to figure out unit oxidation numbers, which will eventually help us tell the oxidation numbers that the questions are asking us for. The oxidation numbers for ions is always going to be the charge on the ions. So if we have, for example, let's take the example that we discussed before. We have phosphate here. So phosphate overall has a charge of -1. So the oxidation number for phosphate is going to be -1. Similarly, if we have another example, for example, let's say we have H+, or we have K+, or Mg2+. So since we know that for ions the oxidation numbers are going to be the charge on them, we will have oxidation numbers of 1, 1, and 2. They're all positive, just like their charges. Now, finding total oxidation numbers from unit oxidation numbers is very easy. So what we basically do is we multiply the number of atoms we have in a molecule with the unit oxidation number. So when we have, for example, phosphate, we know that oxygen's unit oxidation number in this case is going to be -2. So when it comes to total oxidation number, we are going to have a total oxidation number of -2 times 4 atoms of oxygen present in this molecule, so we will have -8 total oxidation number. Other than that, all we have to know before we move on to the example is that group 1 metals like sodium and potassium will always have oxidation numbers of +1, which is basically the group they belong to in the periodic table. And other than that, we will have to keep in mind always that fluorine will always have an oxidation number of -1. That's all basically we have to know for the rules. Now that we're set with the basic rules, we can work with the example we are given. For the first part of the question, we have Ga2O3. And they want us to find the oxidation number of gallium, which is basically the unit oxidation number of gallium. And we can figure that out using the total oxidation numbers. There are two ways to figure out the oxidation numbers. One is the algebraic approach, where you can say that let gallium is equal to X when it comes to unit oxidation number. Okay. So for total oxidation number, we will have 2X because there are 2 galliums here. And then we also have oxygen, where we know that the unit oxidation number of oxygen is going to be -2, and then we have 3 of them. So the total oxidation number is going to be -2 times 3, which is -6. And then next what we do is we look at the charge of the overall compound, and we see that it's 0. So we can say that this is equal to 0 because they should add up to 0. What we end up with is 2x minus 6 being equal to 0. Solving for x, we get x equal to 3. Now this is the answer. Another way to solve for this, which is the way that, or the approach that I highly recommend, is using the Wanton method. This method is very similar to the algebraic approach that we just did here, but it's more organized and simple. So for this method, or the Wanton method, we first write down the unit oxidation numbers that we know or are given. So first we have unit oxidation numbers. So for gallium, we don't know. So we are going to leave that part blank. So for gallium, we don't know what the unit oxidation number is. For oxygen, however, we know that it's going to have a unit oxidation number of -2. Next, we look for the total oxidation numbers. Once again, for gallium, we have no idea, so we are going to leave that blank. Now, we also have, for oxygen, a total oxidation number of 3 times -2, which is going to give us -6. Now, -6 and gallium's total oxidation number should add up to 0, because that's the overall charge of Ga2O3. So, what is a number when added to -6 gives 0? It would be +6. So, we can say that the total oxidation number of gallium is going to be +6. Now, what we have to do next is that we basically go back to our unit oxidation number. It's simple. We have 2 galliums in our main compound, and total oxidation number is the oxidation number of 2 gallium atoms in the compound. So unit oxidation number is basically going to be half of that, so that would be +3, which is the answer that we're looking for. As you can see, this method is really quick and saves a lot of time and space, and also is very organized. Let us look into the next part of the example. Now, before we begin, we can apply the Wanton method and the algebraic approach to do any of these questions, but I will be doing the Wanton method because it saves a lot of space and time and is very quick and efficient. So for part B, we have KBr 04, and they want us to find the oxidation number of bromine, or the unit oxidation number of bromine. So let us list down our unit oxidation numbers first. So for potassium, we know that it's a group 1 metal, so it's going to have a unit oxidation number of +1. Similarly, we also know that the unit oxidation number of oxygen when it's not in its natural state, which is the case here, it's going to be -2. And once again, we don't know what bromine's oxidation number is, and that's what we're looking for, so we will keep that blank for bromine. Now, when it goes to total oxidation number, we only have 1 potassium, so we're going to have a total oxidation number of +1. For oxygen, once again, we have 4 oxygen atoms in this compound itself, so we're going to have to multiply 4 with -2, which is the unit oxidation number, and we will end up with -8. Next thing to do is to look at the charge of the overall compound that we are asked about. And as you can see, it's 0. So that will mean that 1 plus -8, or 1 minus 8 plus something will give us 0. So that is definitely going to be +7, because 7 plus 1 will give us 8. 8 minus 8 is going to give us 0. So we can say that the total oxidation number for bromine here is going to be +7. Once again, we have only 1 bromine in this case, so the unit oxidation number, or the oxidation number that we're looking for, is going to be the exact same as the total oxidation number, and that is our answer, +7. Let us now look into the next part of the example. So for part C, we have NH2 with an overall charge of -1 or minus. And they're asking for the unit oxidation number, or just the oxidation number of nitrogen. So first step would be, once again, to list down the unit oxidation number and then figuring out the total oxidation number. So for nitrogen, once again, we don't know, so we are going to leave that part blank. Next we have hydrogen. So we know that hydrogen has a unit oxidation number of +1, so we can say that here, unit oxidation number is going to be +1. We have 2 hydrogens in this compound alone, so what we're going to say is that we have a total oxidation number of 2 times +1, which is going to be +2. Now, the next thing we do is that we look at the overall charge of the compound that we're given, so we have an overall charge of -1, because we have NH2 minus. So, for total oxidation number, a number that is added to +2 will give us -1. It's going to be -3, because -3 when added to 2 will give us -1. Once again, we have only 1 nitrogen, and hence our unit oxidation number is going to be the same, -3, and that is our answer. Moving on to the next part of the example, or the last part of the example, we have AlOH4 with an overall charge of -1 or minus. Aluminium is the element that they're looking for, and they're asking for, once again, the oxidation number or just the unit oxidation number. Step 1, we will list down what we have. So for unit oxidation number, once again, we don't know what aluminium is in terms of oxidation number, so we're going to leave that blank. We go to the next one, which would be oxygen. Since it's not in its natural state, it's going to have a unit oxidation number of -2. Similarly, for hydrogen, we are going to have a unit oxidation number of +1. Now we move on to the total oxidation numbers. Once again, for aluminium, we do not know, so we're going to leave that blank. We move on to oxygen. We have 4 on the outside of the bracket, so we'll have to multiply that with oxygen, so we'll have 4 oxygen atoms in the compound. So for total oxidation number, we're going to have to multiply 4 with -2 to give us -8. Similarly, for hydrogen, we'll have 4 hydrogens, so we'll have to multiply hydrogen's oxidation number with 4, so we're going to end up with +4. Next, we look at the charge of the overall compound. We see that it's just a minus over here, so we can say that this is going to be equal to -1. Now, what number being added to -8 plus 4 should give us -1? It's going to be +3. You can plug it into a calculator if it's tough, and you'll get that it's +3. Because +3 and +4 will give us +7. -8 plus +7 will give us -1. We have only 1 aluminium in the compound, so we're going to have the same oxidation number. And that is exactly the answer that they're looking for. And this is the answer. As you can see, the Wanton method is very simple and it's very organized, and if practiced a lot will be very useful, and they can be especially useful in long questions with balancing problems. Let us move on to a different example where we can use oxidation numbers and the Wanton approach to figure out oxidizing and reducing agents in a balanced reaction.